More examples. That's the only way you're going to get better. I really would suggest that you stop the video, try to pick something you would compare it to, give it a go, and then come back. All right, again, if we just get rid of all the kind of extra numbers, we would have 1 over 3 to the n. Now, what kind of series is that? That is not a p-series. That is not a p-series. In fact, this is a geometric series where r is 1/3. Remember, you could rewrite this as 1/3 to the n power. And what do I know about a geometric series? If r is less than 1, then I know this converges. So let's try to give the direct comparison test a try. So what I am choosing to compare it to, I'm going to put that on the right. What I'm given goes on the left. And because this converges, which way does that inequality have to go? What I'm given needs to be smaller because of converging. Is that true? Well, you should see that definitely is true because this denominator is bigger than that one, and if the denominator is bigger, then the fraction is smaller. But if you're not sure, you can cross multiply. You just have to keep that in order. So that's 3 to the n. Is that smaller than 2 plus 3 to the n? Yes, that's true. So we can say, therefore, the series does converge by the direct comparison test. A little bit different. Let's look at the next one. Ooh, natural log of n. Don't know anything about that with series. We've got this plus 1, so let's just get rid of everything that we don't really know about, and let's go with this. You just have to try. I know that this is a p-series. In fact, that is that harmonic series, and I know that diverges. So if I try the direct comparison test, I put what I'm comparing it to goes on the right, what I'm given on the left, and since the diverges getting bigger, then I need to show that inequality. That is so not obvious. Let's see if I cross multiply n times the natural log of n. Is that really bigger than n plus 1? Just really don't know. So I'm just going to say not sure about this. So we're going to try the limit comparison test. Okay, so I'm going to take the limit as n approaches infinity of what I'm comparing it to goes on the bottom, and what I'm given goes on the top. Again, you want to simplify that fraction as much as possible, and so if I flip and multiply, I'm going to have n times the natural log of n divided by n plus 1. How do I take that limit? Well, as n approaches infinity, I believe I have infinity over infinity, so I'm going to use L'Hopital's rule, which means I have to take the derivative of the denominator, so that's 1, and the derivative of the numerator, so that's the product rule. So the first times the derivative of the second plus the second times the derivative of the first, which is 1. So let's see, that is 1 plus the natural log of n. So as n approaches infinity, that approaches infinity. Well, what can I conclude about that? That is one of those very special cases. Do you remember what that was? It says, if you get a limit that's infinity and b sub n diverges, the one you chose, and the one you choose on the bottom, then a sub n also diverged. So here we can conclude that the series diverges by the limit comparison test. Very special case. More examples. The sine of 1 over n. What's up with that? again, get rid of stuff you really don't know and just get down to the simplistics. So I'm just going to go with that and see if it works. Again, that's a P series where it's 1. So I know it diverges. I could try the direct comparison test. And again, what I've chosen goes on the right, what I'm given goes on the left, and if this diverges, I've got to show that that is true. Well, if I cross multiply, I would get n times the sine of 1 over n. Is that greater than or equal to 1? So is this true? I wasn't really sure, so I went to a graphing calculator and said, okay, if n gets bigger and bigger, what is n times the sine of 1 over n equal to? Well, at 1 it's undefined, and as it gets really, really bigger, it's getting closer and closer to 1, but is it really ever greater than 1? So I really don't think this is true. It may be eventually true, like it might eventually be equal to 1, but I don't think so. So even if I didn't have a calculator and I couldn't create this table, I just couldn't see that that is necessarily true. So I would try something else. So I'm going to try the limit comparison test. So if I try the limit comparison test, again, what I am comparing it to goes on the bottom, and what I'm given goes on the top. Now if I multiplied, I would get, if I flipped and multiplied, I'd get n times the sine of 1 over n, and I'd have to take that limit, and I'm like, ooh, that's infinity times infinity. So I'm going to need L'Hopital's rule anyway, so I'm going to leave it in this form, and because then I have 0 over 0, and I can use L'Hopital's rule. So now, using L'Hopital's rule, okay, so the derivative of 1 over n is negative 1 over n squared. And the derivative of the sine of 1 over n is going to be the cosine of 1 over n times, again, the derivative of 1 over n. So I know those divide out, and as n approaches infinity, this is going to approach 0, and the cosine of 0 is 1. So after all of that, I finally get a finite limit, and so therefore I can say the series diverges, because remember, it agrees, by the limit comparison test. Okay, we're getting lots of practice. So let's look at this last one. Wow, that looks really different. So again, I'm going to get rid of all the numbers, and I'm going to write this as 4/7 to the n. Is that anything I know? Yes, this is geometric, where r is 4/7, which is less than 1. So it does indeed converge. So if you wanted to use the direct comparison test, we could. And let's see how that works. Right? So if I'm using the direct comparison test, I would have 4/7 to the n, so they would both be to the n. And since this converges, I would have to show that inequality. Is that true? Well, let's see. This numerator is a little bit bigger, but this denominator is a little smaller. If I cross multiply, I would have this, which is kind of ugly. Okay, so can I do anything with this? Well, believe it or not, you could multiply, and this would be 28 to the n plus 5 times 7 to the n. Is that less than or equal to 28 to the n minus 42 times 4 to the n? Well, I would have a positive less than a negative, so that is not true. So the direct comparison test fails. So what can I use? Let's try the limit comparison test. Okay, so we have the same problem, same comparing, but let's use that limit comparison test. So what I've given on top, what I'm comparing it to goes on the bottom, So let's see, that could equal to the limit as n approaches infinity, flip and multiply. That's going to be 7 to the n, 4 to the n plus 5, divided by 4 to the n over 7 to the n minus 42. Well, that's kind of ugly. I'm going to keep plowing along. And so let's see, I can multiply and look at that. Ooh, well, let's see, from cow 1, something about powers, dividing everything by the highest power. So what I'm going to do is I'm going to divide every term by 28th to the nth power and see what happens there. Okay, so when I do that, that's going to become 1, that's going to become 1, not because of the limit, just because you're dividing by the same thing. Could I reduce here? So this it would be 4 to the n on the denominator, and this would be 7 to the n. So as n approaches infinity, that denominator is going to get really large, so that's going to approach 0. Same thing here. So what do I have? Not 0 over 0. I have 1 over 1, which is 1. So now, because I have a finite positive limit, I know the series agrees with my chosen one, and I use the limit comparison test. So now we've added 2 more tests, a little bit harder, and we're not done yet.